Video 34 of the master course, Quantum Chemistry of Molecular Electromagnetic Properties. The topic of this lecture is quantum mechanical expressions for magnetic dipole moments. The derivations for the expressions for the permanent magnetic dipole moments of molecules are quite similar to the case for the electric dipole moment. So I will skip some of the discussions and only try to point at the differences between the magnetic case and the electric case. Let's first look at the expression for the vector potential, because the first thing we have to do is we need to get the contributions to the Hamiltonian from the interaction with the magnetic field, and that is via the vector potential. So we need now the expression for the vector potential and then the first order perturbation to the Hamiltonian. So in chapter 2, we have discussed that the vector potential of a static, meaning time independent, and homogeneous, meaning in space constant magnetic induction, can be written like this. So the vector potential varies in space, but the magnetic induction is constant. Inserting this vector potential then in our Hamiltonian, and there are, remember from chapter 2, there are two places where the vector potential appears. One is the place which was in the kinetic energy term, and one is in that Qcmep term, which we derived from the Dirac equation. So therefore, we also have now two terms here. We have one which has to do with the angular momentum, with the motion of the charges, and one with the spin, motion of the charge, motion of the electrons, and one with the spin of the electrons. And we can write this first order perturbing Hamiltonian again as the product of the field and two operators, which we call the perturbation operators, which depend only on positions, canonical momentum, and here also spin of the electrons. So let's look at this first one, which is angular momentum with the external magnetic field. That's of course the sum over all electrons. And we're going to call it later on the magnetic dipole moment operator. And not only that, we're going to call it the orbital magnetic dipole moment operator, because it is essentially the angular momentum operator for the electrons, for all the electrons, which of course we can write as sum over contribution from each electron, and being angular momentum operator is just R cross P, position vector relative to the gauge origin, vector product with the canonical momentum operator. And the second operator is essentially, apart from some natural constants and a G factor, the operator for the total spin of the electrons. So it's a sum over the spin operators for all the electrons, and here the alpha component of this operator. Taking thus the first derivative of the total Hamiltonian with respect to a component of the magnetic induction and evaluating this derivative at zero magnetic induction is then taking the derivative of the first order perturbation Hamiltonian with respect to that component, and that just gives us minus the sum of those two perturbation operators. And therefore, if we use again the Hamilton-Feynman theorem, we had before defined or derived that the magnetic dipole moment can be written as minus the derivative of the energy of the system in the presence of the magnetic induction with respect to a component of the magnetic induction. So we have to do with the derivative of the energy, and using the Hamilton-Feynman theorem, we can express the derivative of the energy or calculate it as the expectation value of the corresponding derivative of our Hamiltonian. Now that's our minus the two perturbation operators, and since there was a minus sign in front of that derivative, a component of the magnetic dipole moment is then just the expectation value of these two perturbation operators. And now inserting the expression for them, in the first case, we have the expectation value of the orbital magnetic dipole moment operator here, and here we have the expectation value of the total electronic spin operator with some constant in front of it. Or we can write it in this form here, where we have the natural constant in front of it, and then we have the expectation value of the total angular momentum operator of the electrons plus the electronic G factor times the total spin operator of the electrons. And please note that here the spin operator is actually multiplied with the G factor of the electrons, which is 2.002, which means that the spin of the electrons contributes twice as much as a corresponding value of the orbital angular momentum of the electrons to the magnetic moment. Now, I said before that closed shell molecules don't have a permanent magnetic moment, but why is that? Well, we can investigate that now. We can see the magnetic dipole moment has two contributions. One, which is the expectation value of the orbital angular momentum operator. The other one is the spin operator. Because let's look first at the one orbital angular momentum operator. That's an Hermitian operator, which means I can write up this usual expression, which holds for any Hermitian operator. Now, if we consider a system where the wave functions can be written as real, in a real form, the real wave function, then of course I can move the complex conjugate into the operator. The angular momentum operator is a purely imaginary operator, so take the complex conjugate, just changes the sign, and we end up with this expression here, that the expectation value of the angular momentum operator is equal to minus the expectation value of it, and that of course must mean that it's zero. And one says this, the orbital angular momentum is quenched. So the expectation value of the angular momentum operator is zero for real wave functions, and for all systems which have closed-shelled molecules, one can choose the wave function to be real. So for closed-shell molecules or molecules in orbital non-degenerate states, one can choose the wave function to be real, and therefore they don't have a permanent orbital magnetic moment. What about spin? Now, if the molecule is in a singular state, then the expectation value of the spin operator also vanishes, which means there is neither spin nor orbital magnetic moment, permanent magnetic moment. The next question is, there in the electric case, we had also a nuclear contribution to the electric dipole moment, and is there not a nuclear contribution to the magnetic moment? Well, the answer is a bit more complicated here. Of course, the nuclei in molecules can have nuclear spin. Every hydrogen atom, proton, has a nuclear spin. And a lot of other nuclei also have nuclear spin. But the magnetic moments are of the nuclear spin are 3 orders of magnitude smaller, because in the charge magnetic ratio from the spin to the magnetic moment enters the mass of the particle, and since nuclei are at least a factor of 2000 heavier than electrons, their magnetic moments are much smaller, which means we are not going to consider them on equal footing. We will later on in this chapter come back to the nuclear spins and the magnetic moment from nuclei, and there we will just treat them as a perturbation to the electronic energy of the system. So that was the spin of the nuclei. What about the orbital motion of the nuclei, and aren't there any nuclear orbital magnetic moments? Yes, they are, but right now we are in the Born-Oppenheimer approximation, which means that nuclei are fixed in space, so they have no kinetic energy, they don't move, and therefore there is also, of course, no orbital magnetic moments there of the nuclei. Later on in chapter 6 of the book, we come back to that. There we will allow the nuclei to move and to rotate, and there we will then consider the magnetic moments coming from the motion of the nuclei.